Okay, in this lecture, we're going to go over the relationship between line currents or line voltages and phase voltages in the YY three-phase configuration, and we're going to walk through an example problem that asks you to find several variables associated with a three-phase circuit for a given circuit. So if you recall, this is our illustration of a single-phase equivalent circuit. So this would be the A phase of a three-phase YY configuration. We've indicated the source voltage for the ideal source, the generator impedance, the line impedance, and the load impedance. And have illustrated also here the line current, I little a big A, to indicate it's current in the line for a three-phase circuit for the A leg of the phase. So if we look at the load end, because often that's what we're interested in, and we've shown this figure before, there are two kinds of voltages that people tend to define in three-phase. One is the voltage between a given line, so like A, B, or C, and the neutral point N. What's not shown here is that from this capital N at the load end, there is probably a wire connecting that to the generator N, which would be the lowercase n. That's not illustrated here. So since it's only a wire and it's considered an ideal conductor, it's only a node anyway. So the voltages between each line, A, and the neutral are what we refer to as line to neutral voltages or phase voltages. The voltage between two given lines, A and B, B and C, C and A, are referred to as line-to-line voltages or the line voltages. And if we look here, we can see the phase voltages or the line-to-neutral voltages are shown in blue, and the line-to-line voltages are shown in black. So if we wanted to get an expression for one of these line-to-line voltages in terms of the line-to-neutral, then we could do that by writing a KVL equation around these loops. So I would have this loop for the AB voltage, this loop for the BC voltage, and then one big loop around the outside for the CA voltage. And that's exactly what's shown in these equations here. So our VAB is equal to VAN, which is this voltage across impedance A, minus VBN, which is the voltage across this impedance. And that constitutes this one loop. So basically, three equations are written for three different loops, giving the relationships between the phase currents or the phase voltages and the line voltages. Now, if we assume that our A phase has phase angle 0 and that this is a balanced three-phase circuit, we can refer to the magnitude of all of these phase voltages as just phi with a subscript phi. And then the only difference between AN, BN, and CN will be the phase angle. So basically for VAN, we're going to substitute V phi angle 0. For VBN, we're going to substitute V phi angle minus 120, and so on. And so we can write this as a phasor type equation. And if you do the algebra, you find that VAB turns out to be, when you take into consideration this angular relationship, turns out to be the square root of 3 times V phi angle 30. And a similar relationship occurs with VBC and VCA. So if you look carefully, you see that the line voltage is different from the phase voltage by, so for example, the line voltage VAB is different from the phase voltage VA by a magnitude factor of the square root of 3 and a phase factor of a positive 30 degrees. And the same is true for the relationship with VBC and VCA. And notice that once we find VAB, then we can just continue in the pattern to get VBC and VCA by cycling the phase 120 degrees and keeping that factor of the square root of 3. Now if we look at a figure that illustrates the relationships here, you can see here's our phase voltage between the line and the neutral Then the line-to-line voltages are rotated by a positive 30-degree phase angle, and they basically are of a higher magnitude, higher by the square root of 3. So this is a diagram that just indicates, first of all, the top figure indicates for a positive phase sequence, the bottom figure indicates for a negative phase sequence, the difference in relationships between phase voltages and line voltages, or line to line and line to neutral, depending on how you want to state that. So we can use this to get more interesting information out of the system. And I think I mentioned before that when you talk about three-phase in a commercial application, you're almost always talking about the line-to-line voltages, and that's what electricians will tend to measure when they come out and work on your three-phase in your house or in your business. They're often more interested in the line-to-line voltages because that's what's typically running the load. So here is an example of what a single-phase equivalent circuit might look like for a given three-phase system. This is just the figure big enough so that you can see it. Let's go to the next slide. It's going to be the same figure. It's just going to be shown a little smaller. Just to remind you of the terminology, this V little a n is the source voltage. You're including in that the internal impedance, the voltage drop due to the internal impedance of the source, which is illustrated by this impedance between A prime and A. A prime is a virtual node that would give you your ideal voltage source that's not really accessible to the user. The area between little a and big A, this impedance here is the line impedance. It's basically constitutes the transmission line between the generator and the load. Big A to big N is basically your terminals at your load, and this 39 plus J28 would be your load impedance. V big A little n, big N refers to the voltage drop at the load. So you've got a voltage drop at the load, you've got a voltage drop at the source terminals. You also have, not shown here, a voltage drop across the line. That's often not discussed. And then you have a current through the line. And I think we talked before that this is often referred to as the line current, and in a YY configuration of a three-phase system, the line currents and the phase currents are the same. So here's the same circuit with just an example problem, and this is very similar to the kind of thing you would see on an exam. Basically, the problem says you have a balanced three-phase Y-connected generator with a positive sequence. That tells us how to iterate the phase. It tells you the impedance of the generator, and then it tells you its internal voltage. So its internal voltage is 120 volts per phase. It feeds a balanced three-phase Y-connected load that has the following impedance, 39 plus J28, and then it gives you the impedance of the line that connects the generator to the load. It tells you that A phase is specified as the reference phasor. Okay, so what all that means, this little statement that the A phase of the generator is specified as the reference phasor, that tells you up here to put 120 angle 0 for your A phase voltage source, the ideal source. The generator impedance goes right here, as we discussed before. The line impedance goes right here. The load impedance goes right here. So we're asking this problem to find several things, and we're just going to step through and illustrate how to find each thing each step of the way. The first thing to always do in a problem like this is to construct the A-phase equivalent circuit of the system. And so that's done right here. Notice plugging in each important variable into the figure, showing the relevant voltage drops, showing the relevant terminals with the correct labeling. So this is often a problem that I will give on an exam, just to ask people, given the information in this paragraph, can you construct a single phase equivalent? Also of relevance is, can you construct the full three-phase circuit? In order to do that, you would need to show the B phase and the C phase with their associated sources, impedances, loads, and relevant terminals. Okay, the first thing we're asked to calculate are the three line currents, I little a, little b big B, and little c big C. And remember that in in our approach, we're only going to solve for unknowns for the A phase, and then we're just going to iterate everything by 120 degrees. So here's our same circuit again, drawn yet even a little smaller. And to look at the A phase line current, that's relatively simple. This is a single loop circuit with one voltage source. So we can find this current by taking the voltage source and dividing it by the total impedance, which is exactly what's done here, showing the real parts and the imaginary parts of the impedance respectively. We end up with the voltage over the total impedance, and when we convert that to polar form, we're going to get 2.4 angle minus 36.87. And now notice that iterating to the B phase, we're going to subtract 120 degree phase angle, keeping the same magnitude. To the C phase, we're going to add 120 degree phase angle, also keeping the same magnitude. So very simple and straightforward calculation. Part C of this problem asks us to determine the phase voltage at the terminals of a load. So once again, working only with the A phase because we're working with our single phase equivalent circuit. What we want there, phase voltage at the A terminal of the load. What that means is find the A terminal of the load, find the neutral, and the phase voltage is that voltage drop at the load. Now I need to quantify this, saying that that's only the case for a Y-connected load. If we have a delta-connected load, the phase voltage is still the voltage drop across the terminal of the load, but it would not be the drop between A and neutral. It would be a different drop. It's still the drop across the load impedance. All right, so back to this problem. We now have solved for the current in part B. So knowing the current from part B and knowing the total impedance of the load, this becomes a very simple Ohm's law calculation, where we take the current we got from part B and we take the impedance of the load, we find the phasor product, and here's the result. And then notice to find the impedances for the B and C legs, we're just iterating by 120 and negative 120 degrees respectively. Okay, finally, it says for positive phase sequence, we want to find the phase voltages. The line voltages. So the line voltages, remember, that's our VAB, our VBC, and our VCA. So there, we can't really look at this figure because obviously we're not showing the B phase or the C phase. So what we have to remember is the relationship between line voltages and phase voltages. So VAN is our phase voltage, and we know that then that VAB, the voltage between line A and line B, is our phase voltage times the square root of 3 angle 30. So if you take VAN from part C and you plug that into this equation and do the phasor product, you'll get this result. And they only have to do that once because, like the line voltages, the phase voltages iterate with negative and positive 120 degrees respectively. So we can basically just write down the result for BC and CA line voltages based on what we saw for in part C. Okay, finally, we're asked to find the phase voltage at the A terminal of the source. Now remember, that does not mean A prime because A prime is a virtual terminal that we can't really access. What it means is that the physical output of your source, which is the point beyond the source impedance. So basically what we want to do is we want to solve for V little a little n. And the way that's done is a KVL equation is written if you start at the neutral and you come across the voltage source, across the source impedance, and then jump back down to neutral across that voltage drop VAN, you would have a KVL equation. So you would have this 120 is your voltage rise. This parameter here is your voltage drop across this impedance. So it's the impedance times the current, which you saw for in part B. And then you have another voltage drop from terminal A to terminal N that's equal to the voltage we actually want to solve for. So algebraically rearranging the equation, you can set VAN equal to 120 minus the voltage drop across the source impedance. Once we go through and do that one solution and find the phasor product and phasor sum, then once again we can iterate to get the other values. Okay, well, so I want to go back a slide, and I want to look at some numbers. So remember that our source voltage started out at 120 angle 0. So let's come over and look at our phase voltages across the load. Across the load, our phase voltage is 115.2. That's pretty close to 120. And our phase is minus 1.19 degrees, which is pretty close to 0. In a perfect world, you would like to have no losses. So you would like to have all of the 120 angle 0 dropping across the load. So the difference between your ideal source voltage and your phase voltage at the terminal of a load gives you some idea of the losses in the system. So the magnitude gives you some idea of how many resistive losses you had in your generator and your line, and the phase gives you some idea of how much inductance you encountered in your line and your generator impedance. So you're getting a little bit of a phase shift, and you're getting a little bit of reduction in magnitude. Now if we look here at the generator terminals, what this is giving you is the actual accessible voltage. So we actually can't even, say we have 120 angle 0 at the source, because we're losing some of that in the generator itself. So what's really coming out of the source is this 118.9 angle minus 0.32. So that also gives you an idea how close this is to your ideal voltage. Gives you some idea of how much loss you have this time just in the generator. So kind of interesting to look at some of those numbers. Okay, so that's going to be everything for this lecture, and we will look next at the delta connected load.